All right, so I promised you a rant on machine learning, specifically in the industrial space. And so, what I'm going to try to go through here in sequence is number one, I'll talk about my first experience with machine learning, why I'm a big believer in it, why I think it can do wonders. Then I'll go through what I call the pre-LLM era. I'll talk about the big three types of machine learning systems you could use. Pre-LLM. Turns out they happen to be really applicable today too, but let's go through them because they were what was famous before LLMs. And then we will recklessly prognosticate about the future and what could happen now with LLMs in addition. So if that works for you, I'm just going to roll into my rant. Awesome. So my first exposure to machine learning was in grad school. And I was studying, the topic I'm studying is not so important, but it happened to do with acoustic absorption inside of polymer foams. And it turns out that that's a very stochastic process in manufacturing, which simply means any two times you manufacture this particular material, it's going to come out slightly different. And therefore, they needed some type of advanced way to model what would the sound absorption be. And so, long story short, for the purposes of the tutorial, my first goal, this was my master's thesis, my first goal was just do a linear regression. I know lots of stuff about the material. I know the density, I know the weight of it, I know the percentage porosity, things like airflow resistivity. There was a whole host of things that I knew about the material itself that I could test empirically. What I didn't know is the direct physical relationship between that and the sound absorption, which is what I really cared about in this research. So step one, just linear regression. Assume that there's a linear relationship between all of those variables and the output that I was looking for. Do a standard regression and see how it works. And it worked poorly. It was a very poor regression. In the world of regression, you look at R squared values that let you know how good your results are. And so R squared values were on the order of zero point 0.5, zero point 0.6, not good enough for scientific work. So then I said, okay, nonlinear regression. Nonlinear regression is probably going to be my savior here. And nonlinear regression, it's not that much harder. The only difference from linear regression is instead of having literally one linear term, you can add in all kinds of fun functions that you learned about in grade school. So like trig functions, sines, cosines, exponentials, squared values, all of those are off limits in linear regression. They are not in nonlinear regression. So I attacked it with nonlinear regression. And the results didn't get that much better. Got R squared values in the zero point 0.6 to zero point 0.7 value. Anyone that does regression will say that's not impressive and certainly not publishable. There's nothing there that's worth writing a paper about. And so finally, I backed into neural networks. I thought I was studying acoustics. I ended up sinking all of my time into neural networks and machine learning. And long story short, with a dead simple three-layer backpropagation neural network, I was able to get regression values or R squared values of 0.95, 0.96, and eventually we pushed it to 0.99. Long story short, I could have saved a ton of time. It was a genuinely magical thing. I didn't even have to specify the functional relationship between inputs and outputs. It was very much a black box, but the software that I was using right out of the box, I used the standard model, the one that you would study in chapter 2 of a neural networks textbook, and boom, it worked like crazy. I had my publication. I was so relieved because I was going to graduate and life was good. That was, I'm dating myself. That was a good 20 years ago now. That was when I really came to believe in the value of neural networks and more broadly machine learning. And so now I love studying it in the industrial space. I'll divide this tutorial into pre-LLMs and post-LLMs because they're very different ways of approaching machine learning. So right now, let's you and me skyrocket to the years like 2015 to 2020, right around then. Back in those simpler days, there were really three ways that you could attack machine learning. And broadly speaking, that was expert systems is number one. Number two was unsupervised learning. And number three was supervised learning. And I'll go through what each of them is in a medium amount of depth. Enough that there's some real meat here, but not so much that I'll bore you with calculus. So expert system first and foremost. That's a very old-fashioned term. People have been trying to develop these for many decades now. And what they simply imply is that an expert knows certain things about a system. They can codify those into either rules in the case of like a medical doctor or to direct physical relationships in the case of an engineer engineer that's trying to map inputs and outputs and knows the physics behind the situation. And so expert systems in theory are very straightforward. You're building a massive decision tree that says, I know these physical realities about the input output relationships, and I'm going to map those into a massive decision tree. And there I have it. I've got an expert system. Give me any input. I'll give you the right output, and life is great. It turns out that they work really well for tiny bounded problems. They do suffer from the curse of dimensionality. As soon as you get into a large number of decision trees, they become super brittle and they're really hard to maintain. So they handle edge cases very, very poorly, but they have their place. And so I still encourage everyone to use them today. They're one piece of your arsenal. They're not the only thing you would ever use, and they are admittedly an old-fashioned method, but they're one piece of the puzzle. And so never hesitate to just put together a simple decision tree based on physics laws that you know about the situation that you're dealing with as one of multiple ways to attack the problem. So that's what expert systems do. Next, let's go to unsupervised learning. Unsupervised learning, as the name implies, is when you're researching about a system, but you don't know the predicted outputs in advance. In a moment, we'll contrast that with supervised learning when you do, but let's stay on unsupervised. So you have a system, it has many different possible inputs. That's the data set that you've got in hand. What you don't know is the outputs of this particular system, and that's what you're trying to figure out. But you're making it hard on the method because the method has no idea what the outputs are. You have nothing to train it on. There is no training. By definition, this is unsupervised learning. And so it's best to think of these algorithms as clustering at their heart. Clustering is one specific subcategory of unsupervised learning. The other one would be dimensionality reduction techniques. But big picture, what all unsupervised learning is doing is they're trying to take your data set and put it into logical clusters or segments, and then let you know, hey, you handed me a big messy pile of data, many dimensions, many different variables. You should know that these 7 segments seem to be meaningful. And that's what the algorithm is doing. Multiple algorithmic approaches, but the algorithm is segmenting into X different buckets. And interestingly, the user has control. In a method like k-means clustering, the user controls that. You tell the algorithm, you know what? I think it's 5. I think the number is 5. Please assume there's 5 clusters in this data and go to town. Do the statistics. Tell me what those 5 clusters are. The big advantage, obviously, on unsupervised data is you can feed any data set into it. Because you're not training, the sky's the limit. You can literally feed in anything. You need to have zero a priori knowledge of the situation that you're dealing with, because the whole idea is that the algorithm tells you the clusters. And so I tend to use these for anomaly detection algorithms. So you do pay for this big benefit. The benefit of knowing nothing about the system, you pay on the back end because all you can do is detect anomalies. And the way you detect anomalies is the system says, normally those inputs would map to a particular output. And right now, that's not what's happening. Like something in cluster 1 is now steadily migrating over to cluster 4. That's a problem. And right there is where you pay, because that's a very abstract thing to say. And, engineers and technical specialists like you and I, we're always dealing with a very concrete reality. We're trying to optimize a process. We're trying to identify a failure mode. Cluster 1 and cluster 4 are meaningless abstractions. And so all that unsupervised learning will tell you is you have a problem, you have an anomaly. It will give you no information about the nature of that anomaly and what exactly is happening. And that's the price you pay for basically not having any training data, not knowing the input-output relationships. So again, unsupervised learning has its place. It's your first go-to if you just don't know what the heck to do with this data set. Never hurts to at least do some clustering on it and monitor over time the particular system in question to look for anomalies. And the downside is once you get the anomaly, it's on you. You got to figure out what the heck is happening. The algorithm won't tell you. So that's unsupervised learning. when we move to supervised learning, this is a case where you have multiple data inputs, multiple streams of data, and you know the desired outcome. You probably don't know the direct functional relationship, like the whole reason you've come to unsupervised or to supervised learning in the first place is you can't model it with physics. Like you tried, you would have done that if that was option. That's much easier and quicker. Instead, you take a system with a number of inputs and you do know the output because the system output is something that you're measuring and is inherently part of the data set that you're messing with here. What you don't know is the relationship. And your goal with supervised learning, first and foremost, is to train the algorithm, most commonly a variant on a neural network, but to train the algorithm to learn that highly nonlinear relationship between inputs and outputs. And then therefore you can predict what will happen in the future for a yet unknown set of inputs. So you can do modeling, you can do simulations, you can say, this is not happening in physical reality right this moment, but I want to simulate some stuff and see what the system would do in those weird corner case scenarios. And supervised learning tends to do really well with corner cases, so far better than expert systems that break down immediately as soon as you start to get into the corner spots. And so supervised learning is really the deepest workhorse when you need a direct relationship between inputs and outputs. There are two kind of big ways to go about it. One is referred to as regression, and one is referred to as classification. In industry, we tend to run into the regression version more. And these two things simply refer to when you're doing a regression approach, you're trying to identify a parameter that has a whole spectrum of values. Might be a pressure, a temperature, a level in a tank, a flow rate, an overall energy consumption of a particular system, the yield in a reaction, whatever it is. These things are continuous variables, if you will. There's a whole spectrum of values, and what you're doing with the regression, this supervised machine learning approach to regression, is being able to feed an algorithm the inputs and know in a very quantitative way what the outputs will be, even if that algorithm has never seen those exact set of inputs before. Hence, advanced process modeling. Perfect for advanced process modeling. Really good for that application. And then classification is simply a discrete version of that. It's less common in my experience in the industrial space, more common in things like marketing space, which is outside of the domain of the things we're talking about here. But in the marketing space, for example, you'd be predicting, will a consumer take action A or B or C given this set of inputs that is fed to them? And that would be better described as a classification tasks. What pre-existing behaviors or pre-existing views of a particular viewer would lead them to buy products A, B, or C. And then you map in, hey, here's a new customer. These are the inputs. What are they going to buy? A, B, or C? Which one's it going to be? It's called classification because there's a finite set of discrete outputs. In this case, just 3 things that they may or may not buy. Those are the big ways to think about supervised learning. And I use regression much more often than classification. I find it's just a much more common thing in the industrial space. Those are the big 3. I'll reiterate them briefly. Expert systems is where you know some physics laws or you have some expertise about the system, and all you're doing is hard coding that expertise into an algorithm, almost always a decision tree. The vast majority of times it's a decision tree. The pro, you can embed a little bit of knowledge and it's really cool and it works well for tiny bounded problems. The con, it blows up in complexity very quickly. And so it's terrible at corner cases and it's terrible at bigger problems. It's really only for toy problems or tiny bounded problems that it turns out to be a good method. Then you go to unsupervised. So method number 2 was unsupervised learning. We don't know anything about the system. Never fear. The algorithm will segment the data set for you and they'll tell you, hey, if you had 5 segments, this is what it would look like. If you had 7, this is what it would look like. And then you get the virtue of, for free, you can spot anomalies when your system is drifting in a way that is anomalous to prior baseline behavior. The downside, who the heck knows what that anomaly is? It is not at all meaningful in the physical world to say we've moved from cluster 2 to cluster 7. You can't map that to a pump and say the pump has a bad bearing. And so that's the downside. You got to do the work yourself. And then supervised, the big workhorse, you have both the inputs and the outputs. You train up the thing, and then the model, almost always a neural network or a sophisticated variant on top of a neural network. It will tell you either the continuous value of a parameter. That's most often what we're doing in the industrial space, or a discrete value, which is much more common in, for example, the marketing space, where you want to predict future actions of a person. And there's really only like 3 to 5 discrete things they might do in this particular model. And that is my whirlwind tour through machine learning. Now, notably, the reason I wanted to make sure I talked about that before LLMs is that, for my money, there's still a lot of low-hanging fruit there. I don't think that our industry's work is done for deploying those 3 tools. And so we'll come to LLMs in a second, but my encouragement to everyone that's working in the space is there are plenty of problems still waiting to be attacked by all of those methods. And so don't give up on them yet. Doesn't mean you can't use LLMs, but there's plenty of work left to do with these reasonably standardized and well-documented algorithms from each of those 3 machine learning categories. And so for me personally, I intend to be swimming in those 3 categories for at least another decade. And there's lots of good work to do there. Maybe a couple of shout outs. For one example, the 2 big applications in our world is predictive maintenance and process optimization or process control. So on the predictive maintenance side, I confess that I'm biased because I've worked very closely with Team Weights for a while, but Weights is doing really amazing things on using machine learning to identify faults in machinery for condition monitoring purposes. And so any listeners may want to just go check out what Weights is doing, kind of study their work. That's a really good example of using all of these machine learning methods for a condition monitoring, i.e. prediction of failure mode application. Another gentleman I really respect is Ken Sanderson. Has been in the trenches for a long time, working on the toughest process optimization challenges using an agentic approach to AI, which underneath the hood is using all of the stuff that we just talked about now. It's just deploying multiples of them in an agentic fashion, depending upon the state of the process. So consider what he's doing, a really clever combination of many classical and also reasonably new machine learning techniques. I've always admired that. I think he says he's done over 200 individual case studies. Like, he's in the trenches, he's doing the work. He's one of the very few people that are really attacking agentic AI in the industrial space. And so I have a lot of respect for Ken Sanderson. I've read a lot of his work and highly recommend it if you're interested in these things. Go check out the work of Ken Sanderson. And he happens to be the founder and CEO of Composable. Composable is the company that he's now using to implement his methodology. But yeah, those are my 2 favorite applications for machine learning: predictive maintenance and process control. And as any new controls engineering graduate will tell you, there is a ton of runway left in process optimization. The vast majority of control loops out there is single input, single output, PID controller, and that's it. And the PID controller isn't even like optimized using all those cool algorithms that we were taught senior year in school. And so, as I've said before, control engineers everywhere are like banging their head against the wall because they studied late night convex optimization stuff with multidimensional inputs and outputs and nonlinear systems. And then they get into industry and everything is single input, single output control loops. I exaggerate when I say everything, but let's call it 80%. 80% of the loops out there are just single input, single output. So long story short, I respect Kent's a lot. Good dude to check out. He's doing the hard work of stepping the industry up to the next level on process controls and process optimization. And then now we would pivot to the fun part, which is LLMs. So for me personally, I think LLMs are a miracle. I use them multiple times a day, every single day. I use multiple of the commercially available ones. And the experience for me, it's like having a brilliant friend who knows the basics of literally every possible area of human knowledge and can articulate them to you in a really concise manner. And then even better, in my case, one of my personality quirks is I like to dive 7 layers deeper than any reasonable person would want to do on certain topics. And so it annoys the heck out of human beings, but the chatbots don't care. They let me ask questions all day long. And I ask the same question with like 7 different nuances, and they never get annoyed. They just keep spitting out more and more insights to me. So I am a full-blown, I believe LLMs are a miracle. I've never experienced anything like this. And so I am 100% certain that they will be revolutionary in the industrial space. Having said that, I'm also quick to say I'm seeing very little impact so far. There are plenty of ideas, plenty of early stage pilots for trying to deploy LLMs in industrial applications. But based on my experience, they're nowhere near the effectiveness yet of the three types that we talked about before: expert systems, unsupervised learnings, and supervised learnings. I don't know the future of LLMs any better than anyone else does. It's plausible that they will come to be the dominant method for like hardcore high dimensional data analysis. But I do want to ground everyone that it's not that today. What that would look like for me, there's a thing called MCP, Model Context Protocol, that everybody's talking about. It's basically a way to standardize the way that a pre-trained, pre-existing large language model would interface with a custom data set of the type that a plant or a manufacturing organization would have inside of their own four walls. And so for the moment, that has the most promise. Time will tell if MCP becomes the standardized protocol. Many people are predicting it is. It's not so big a deal whether it's MCP or something else, but the hard work that will start now and probably be a lot of work over the next 5 to 10 years is pointing pre-trained LLMs at more and more unique data sets and proprietary data sets that reside inside of the factory's four walls. That's where all the fun stuff is going to happen, and we're just very early days. Lots of promise, but the slight wet blanket is I've not seen a killer economic impact from LLMs looking at hardcore industrial data yet. I'm certain that they will come, but we're just not quite there yet. One really promising application called Timebase, and they just in the past week or two released the fact that they've got an MCP server that sits directly on Timebase. That's pretty darn exciting. So Timebase holds all sorts of technical data, just like any other plant historian would. And now you have an MCP server pointed directly at Timebase. That could be really exciting. There could be a lot of applications that hit really in the near future. That's not a future-looking thing. That's available today. You can go check and play with that today. So long story short, of course, LLMs will be one of the dominant methods that we use to gain insights in predictive maintenance, process optimization, advanced modeling, all of those applications. For sure, LLMs will play some role, and I'm sure I will use them too. My simple admonition to everyone is don't forget about the other big three. There's still plenty of really great work that is completely appropriate for those methods, and don't forget about them. They're great. They're maturing. Everybody knows how to use them. Lots of packages like PyTorch, and don't forget about old school machine learning. And yeah, that's my rant. If that topic is of interest to anyone, you would do us a great service if you would like and subscribe to the channel. And we plan to continue pumping out lots more content just like this. Let us know your thoughts. Can't wait to engage.